Welcome to session 13, which happens to be the last session of UGBS 301. In this session, we are going to consider correlation and regression. These are what we call measures of association, and we shall identify how two variables relate with each other, and based on that, we would extend to regression analysis, where we would focus on predicting the values of one variable based on another variable. By the end of this session, you should be able to draw and interpret a scatter plot, calculate and interpret a simple correlation between two variables, determine whether the correlation is significant, calculate and interpret a linear regression equation for a set of data, understand the assumptions behind regression analysis, determine whether the regression model is significant or not, and to use Microsoft Excel to calculate correlation and regression coefficients. We start with a scatter plot. A scatter plot is a diagram that actually shows the relationship between two variables. And a scatter plot can help us to find the level of correlation between two variables. When we say correlation, this analysis is actually used to measure the extent or the strength of the association. And when I say association, I mean the linear relationship between two variables. Correlation is noted to be concerned only with the strength of the relationship and not any causal effect. So we believe that if the correlation among two variables is high, it just tells us that one variable is highly related or associated with the other variable, but it doesn't tell us that the occurrence of the other variable is caused by the presence or the absence of the particular variable in question. These are some examples of scatter plots. The ones that looks like a straight line actually are linear relationships, and the ones that look like the curved ones are what we call a curvilinear relationship. For the purpose of this course, we will be more concerned with linear relationships. A linear relationship can be strong or weak. In these first two examples, you could see that the scatter plot shows a more narrower plot, which indicates a stronger relationship between the variables y and then variable x. This one shows a very broader curve, a broader plot, and it indicates that the linear relationship is quite weak. That is, the relation between y and x is weak. In this situation, we can see that there is no relationship at all because it doesn't follow any linear format. The correlation coefficient is something that helps us to also determine the strength of the association between the two variables under question. The sample, we have the population correlation coefficient and the sample correlation coefficient. Therefore, if we are dealing with the population data, we are going to look at the population correlation coefficient. If you are dealing with the sample data, we would use the sample correlation coefficient R to estimate the population coefficient rho. These are some of the features of the correlation coefficient. It is unit free, that is, it's not measured in any unit. It ranges between 0 and 1, and the closer it is to 1, sorry, let me take this slide. These are some of the features of the correlation coefficients, that is for rho and then for R. It is unit free, that is, it is not measured in any unit. It ranges between -1 and 1. The closer it is to -1, you say the stronger the negative linear relationship, and the closer it is to +1, the stronger the positive linear relationship. Also, the closer it is to 0, whether positive or negative, the weaker the linear relationship. We also note about the strength of the relationship. These curves actually indicate some of the strengths. you could see that this is a perfect negative correlation. Everything falls on the straight line, and the values or the dots are arranged on that line perfectly. It tells you that y is perfectly related to x. We also have a moderately strong negative relationship between y and x, and it's giving us a correlation coefficient of negative 0.6. In the third example, we have a correlation of 0. That indicates no relationship between y and x. A correlation of a coefficient of 0.3 positive. That indicates a positive correlation, but it is weak. And then we have that of 0 in the last example, which gives us a correlation coefficient of 1. That also shows a perfect positive correlation between y and x. In terms of the direction, whether negative or positive, these signs actually just tells us the direction and not necessarily the strength. So, in a negative correlation, we see that as the values of x increases, the values of y reduces, and vice versa. But for a positive correlation, as the value of x increases, the value of y also increases. There are some ways to calculate the correlation coefficients. Mathematically, the sample correlation coefficient is given as the covariance between x and y divided by the variance of x and then that of y. That is sxy over sx times xy. Computationally, the correlation coefficient for the sample is given as the summation of x minus x bar times that of y minus y bar, where x bar and y bar are just the sample means of the x and y variables respectively, divided by the summation of x minus x bar all squared times the summation of y minus y bar all squared, all under the square root sign. We will take an example, and I know it will help you understand this formula very well. Let's take this example where we want to find whether there is some level of association between the number of commercials denoted as X and the number of sales volume denoted as Y. In other words, do we see that if number of commercials increases, does sale value also increase? Or if the number of commercial increases, does sale value also volume also decrease? Or maybe there's no relationship at all. In so doing, let's look at the formula once again. We said that R, which is our correlation coefficient, is the covariance between X and Y, which is giving us the summation of X minus X bar times the summation of Y minus Y bar divided by N minus 1. Therefore, in doing so, you see we have a new column that shows X minus X bar, and then another column that shows Y minus Y bar. X bar is the sample mean for the X values. If X has a total score of 30, then the mean will be 30 divided by the size of the sample, which is 10. Therefore, we have a mean of 3. So for each item or for each week, you see that we have here it will be 2 minus 3, that gives us negative 1. 5 minus 3, that gives us 2. 1 minus 3, that gives us negative 2. 3 minus 3, that gives us 0, and so on and so forth. We do similar for Y minus Y bar. That is, we have a total of 510, giving us a mean of 51. That is 510 divided by 10. And then for each, we have 50 minus 51, giving us negative 1, and so on and so forth for the rest of the 10 samples. Then in the next column, we multiply x minus x bar scores with y minus y bar scores. So we have minus 1 times minus 1 giving us 1, 2 times 6 giving us 12, negative 2 times negative 10 giving us 20, and so on down to the sample number 10, that is negative 1 times negative 5, that gives us 5. The summation of that gives us the numerator value, which is 99, divided by n minus 1, which is 99 over 9, that is 11. That gives us the first part, which is the SXY. We can also do similar for the S of X, that is the standard deviation of the X values, which is also calculated as the summation of xi minus x all squared, x bar all squared, divided by n minus 1 under the square root sign. Therefore, we're going to have another situation where we have x minus x bar, that is already given. This time we are going to square it, that is x minus x bar all squared. So you see that all the x minus x bar values are squared. That is 1 squared, negative 1 squared gives you 1, 2 squared gives you 4, negative 2 squared gives you 4, down to sample number 10, that is negative 1 squared, that also gives you 1. We do the same for y minus y bar, that is negative 1 squared gives us 1, 6 squared gives us 36, negative 10 squared gives us 100, down to negative 5 squared, that gives us 25. So you see that the sigma x minus x bar all squared gives us 20, giving us 20 over 9, taking the square root, that is n minus 1, taking the square root, you have 1.49, and then that of y minus y bar all squared also gives us 566 over n minus 1, which gives us 7.93. So from this formula, sxy over sx times xy, then it means that we are going to have 11 over 1.49 times 7.93, which gives us a correlation coefficient of 0.93. Alternatively, what we can also do is we can use this same formula to find the correlation coefficient. In other words, we already have our x minus x bar, y minus y bar already given, which is 99. Also, we have our x minus x bar squared, and then y minus y bar squared values also given to us, that is 566 for the y's, and then 20 for the x's. All we just need to do is to put the values in this formula. That's going to give us 99 divided by the square root of 20 times 566, and you'll be sure to get 0.93 as your correlation coefficient. In this, we can therefore conclude that there's a strong positive correlation between the number of commercials and then the sales volume. Thus, we believe that as you increase the number of commercials, that is the adverts that you make, your sales volume would also increase. These are also other computational formulas in calculating the correlation coefficient. One other way to calculate the correlation coefficient is just to look at the summation of the xy minus summation of x minus summation of y all over the square root of n summation of x squared minus summation of x all squared multiplying n summation of y squared minus the summation of y all squared. R is given as your sample correlation coefficient, n is given as your sample size, x are the values of the independent variable, and then y are the values of the dependent variable. For example, assuming you want to find the relationship between the tree heights and then their trunk diameter, where y is the tree height and then x is the trunk diameter, at one point we are going to multiply the values of x and y. So we create a new column. that is xy. So 35 times 8 giving us 280, 49 times 9 giving us 441, and so on. Then we put them together and we get 3,142. We also do the same and calculate y squared, that is squaring all the y values. So 35 squared giving us 1,225, 49 squared giving us 2,401. Putting them all together, we get 14,111. We do similar for x squared. 8 squared giving us 64, 9 squared giving us 81, 7 squared giving us 49. Put them all together and we have 713. So based on this formula, we have our sigma xy, we have our sigma y squared, and we also have our sigma x squared. We have our sigma y, and then we have our sigma x. So our sigma xy is 3,142 times n minus our sigma x, that is summation of x giving us 73 times that of y giving us 321, all over the square root of the sample size of 8 times sigma x squared, that is 713, minus sigma x all squared. You need to take note of sigma x squared and then sigma x all squared. Sigma x all squared will be 73 squared, whereas sigma x squared is 713. So we have that minus 713 times 8 into sigma y squared, which is 14,111 minus 321 all squared. This gives us a correlation coefficient of 0.886. That tells us that we have a relatively strong positive linear association between x and y, that is our tree trunk, our trunk diameter, and then the height of the tree. In Excel, you can also use it to Excel can also help you find the correlation coefficient. Under the data analysis tool, using the analysis tool pack, there are ways to find the correlation coefficient. And the Excel output is given us here, as shown here, giving you the relationship between the trunk diameter and then the tree trunk. Now, this entire table is what we call a correlation matrix. You see that for the tree height, and then the tree height itself is a perfect correlation because it correlates with itself. The trunk diameter and trunk diameter also gives you a perfect correlation. Then we have trunk diameter and tree height, that is 0.886, that's what we had here. And then we can also do tree height and trunk diameter, whose value would also be the same as 0.886. Given these correlation coefficients, we note that these are just based on sample values, and hence we believe that we need to test the significance of this level of this association to infer to the population. Therefore, we test some hypotheses. So, our null hypothesis will be that there is no correlation between the two variables, which will state that our rho, or our population correlation coefficient, is 0, against the alternate hypothesis that a correlation exists, which will actually test the hypothesis that rho is not equal to 0. We're going to have our test statistic, which is actually a t distribution, which is r over 1 minus r squared divided by n minus 2 under the square root sign. And this is a t distribution with n minus 2 degrees of freedom. Let's take an example. We want to find whether there is a linear relationship between tree height and then trunk diameter at the 5% level of significance. Therefore, we formulate our null hypothesis, which indicates no correlation, that is rho equal to 0, and then the alternate hypothesis, which indicates that correlation exists, that is rho not equal to 0. We have an alpha value of 0.05 degrees of freedom, of 8 minus 2, that is giving us 6. And hence our test statistic is r over 1 minus r squared over n minus 2, that is under the square root. And based on that, we get 4.68. Our critical value is t alpha over 2 n minus 2 degrees of freedom. And based on that, because this is a two-tailed test, we are going to have plus or minus 2.4469. Just as we did in the case of the hypothesis test, we are going to test whether this value, the test statistic, falls in the rejection region or within the acceptance region. As we can see, our 4.68 is way bigger than 2.4469 and hence falls in the rejection region, and therefore we are going to reject our null hypothesis that states no correlation and conclude that there is an evidence of a linear relationship at the 5% level of significance. The correlation, as already said, just allows you to measure the level of association, how the two variables are related to each other. But it doesn't help us to predict or explain the impact of changes. Therefore, we move on to the regression analysis. Regression analysis will help us to predict the value of what we call a dependent variable based on the value of at least one independent variable. It's going to help us to explain the impact of changes in an independent variable on a certain dependent variable. By way of explanation, when we say dependent variable, it means the variable that we wish to explain. When we say independent variable, it just means the variable we would use to explain the dependent variable. So more likely, we will say that the dependent variable actually depends on the independent variable. There are various kinds of regression models. We have a linear regression model, we can have logistic regression models, we can have various forms of regression models, but we will deal with the linear regression model, and under the linear regression model, we shall deal with a simple linear regression model. In this model, you have only one independent variable and then one dependent variable, and then the relationship between x and y, that is our independent variable and our dependent variable, is described by a linear function. We believed that here there are some levels of causality, and hence changes in the dependent variable are assumed to be caused by changes in the independent variable x. These are various types of regression models. You can have a positive linear relationship, a negative linear relationship, a relationship that is not so linear, and then a no relationship at all. This is how our regression model looks like, the simple linear regression model. As already indicated, y is our dependent variable and x is our independent variable. We have coefficients like beta 1, which is attached to the independent variables, and is mostly called the population slope coefficient, or the slope. We also have the population, the y-intercept, and then we have what we call the random residual, or the error term. Thus, our regression model is giving us y equals beta naught plus beta 1x plus epsilon, also known as our error component. These are some assumptions concerning the linear regression model. Error values are statistically independent. They are normally distributed, and that is their probability distribution is normal, and they have a constant variance. And the underlying relationship, as already indicated, between the x variable and then the y variable is a linear relationship. This is also a graphical representation of our model, where, as you can see, the model fits a line that indicates the relationship between our dependent variable and then our independent variable. The slope of the line is given as the coefficient of b1, and the error term is given as the difference between the actual value of y versus the predicted value of y. Based on this model, we can estimate a population regression line based on our sample. Therefore, based on the sample, our predicted y value will be y capped. Over here it was just y. Because we are estimating, we are going to have y cap is equal to, now the beta in terms of the population has changed into b. That's for the sample, which is an estimate of the regression intercept, plus beta 1, b1, which is also the estimate of the regression slope, times the independent variable x. In this estimated regression, there is no error term. That is, the individual error terms have a mean of 0. Therefore, in trying to obtain the values of b0 and then the values of b1, we use what we call the least squares criterion, which tries to minimize the sum of squared residuals or errors. Based on the least squares equation, our estimated value for b1 is given as summation of x minus x bar times y minus y bar over summation of x minus x bar all squared. Computationally, we can also have summation of xy minus summation of x times summation of y divided by n all over summation of s squared minus summation of x all squared over n. Whereas b0, or the intercept, is also given as y bar, which is the average of the y values, minus b1, which is the estimated slope, times x bar, which is the average of the x values. So these are the formulas for beta 1, as we've already seen, and that of beta 0. Let's see how we can interpret these values. The beta naught, or b0, is the estimated average value of y when the value of x is 0. So whatever value we get for beta naught is just the value of our dependent variable if our independent variable is 0. Similarly, b1 is also the estimated change in the average value of y as a result of a 1 unit change in x. You'll understand this better when we take the example. So let's try to find the least squares equation. You can use softwares like Excel, Minitab, SPSS, and so on to find the values of b0 and b1. And you can also use this formula to also find the values of b0 and b1. We take an example. We have a real estate agent who wishes to examine the relationship between the selling price of a home and its size. We have a random sample of 10 houses and then their house prices as well as their size of the houses given in terms of square feet. Therefore, let's say for one we have a price of 245,000, then a square feet of, or a size of 1,400 square feet, on and on till the last sample. You want to find out, in this situation, you have to indicate what your dependent variable is and then what your independent variable is. Intuitively, we know that we are finding whether the price of your house depends on the size of the house, and therefore Our dependent variable is the house price, whereas the independent variable is the size of the house given in terms of square feet. You can use the Excel approach to solve this under the data analysis format. We have regression 2-pack that will help you to do this. And based on that, you have this output. That's the Excel generated output. That gives you a lot of information. But at this stage, what you are more concerned with are the regression coefficients. So you have an intercept which actually corresponds to the B0, and then the square feet side, which coefficient actually corresponds to the B1 estimate. Therefore, our estimate of the house price is given as 98.248, that's the value of B0, plus 0.10977 times the square feet, that is the size of the house, given as the B1. So based on this sample, this becomes our estimated regression equation. In terms of graphical representation, this is how we can represent it. This is the fitted line, and these are the actual values. That is 0.10977 becomes the slope of the line. So house price now is given as 98.24 plus 0.109 times the number of square feet. In terms of interpretation, we would say that since we said that beta naught is the estimated average of y when the value of x is 0, then what we mean is that if square feet is 0, then the price of the house will be 98.24. Sometimes this one doesn't really have much of an interpretive value because no houses will have 0 square feet. And therefore, we can just say that for beta not equal to 98.24, it just indicates that from the houses within the range of sizes observed, 98,248.33 is the portion of house price that is not explained by the square feet. Remember that the house price was given in terms of thousands, and that is why we've multiplied our 98.24 by 1,000. But what is of more importance is the interpretation of the B1. We said that the B1 measures estimated change in the average value of y as a result of a unit change in x. Therefore, if you have a B1 of 0.10977, it tells you that for every unit increase in the square feet, you're going to have a 109.77 increase on the average on the house price. Also, remember that this was already given in thousands, and therefore, if you're interpreting, you have to multiply this value by 1,000. So we say that here, B1 equal to 0.10977 tells us that the average value of a house increases by 109.77 on average for each additional 1 square foot of the size that is added. We can also move away from the Excel generated output and try to find or calculate these coefficients by hand. Remember the way we went through when we were doing the correlation analysis? You go similar way in terms of this regression. That is, you have to create a column that looks like x minus x bar, another one that looks at y minus y bar, then another column that brings about the product between x minus x bar and y minus y bar, and then another one that looks at x minus x bar squared and y minus y bar squared. You put in all the summation and it will help you calculate the value of the coefficients by hand. In terms of this regression analysis, the total variation of the regression analysis has been grouped into two. That is the explained variation and the unexplained variation. The explained variation are the ones that, or the part of the variation that can be accounted for by our regression model. That is this one. And then the unexplained variation are the ones that cannot be accounted for by our model. Explained variation can be measured in terms of the sum of squared regressions, and then the unexplained variation is measured in terms of the sum of squared error. Explained variation is sometimes given as SSR, and then unexplained is SSE, whereas the total variation is SST. SST is given as y minus y bar all squared. SSE is given as summation of y minus y cap all squared. And then SSR is given as summation of y cap minus y bar all squared, where y bar is the average of the dependent variable, y is the observed values, and then y cap is the estimate of y given the x values. So that is what we've said. Total variation is the total sum of squares measured by SST. Error looks at the unexplained variation, and then regression sum of squares look at the explained variation. Based on this, it can help us to calculate the coefficient of determination, also known as the R squared. The coefficient of the determination is explained as the portion of the total variation in the dependent variable, which is explained by the variation in the independent variable. In other words, the coefficient of determination is the portion of the total variation which is explained by your regression model. The coefficient of variation is given as the R squared, which is equal to the SSR over the SST. Thus, the regression sum of squares over the total sum of squares. This gives you a value whose range lies between 0 and 1. Note that for a sample, we have the capital R squared giving us small r squared, where our R squared is the coefficient of determination, and then R, very familiar, is seen to be our sample correlation coefficient. Therefore, we can say that the square of the correlation coefficient will give you the coefficient of determination. So as you can see in this Excel generated output for our last example, we had multiple R. We had the R squared value, that is 0.58082, which was actually given as the sum of squares regression, that was given as 18934, also given in the output, divided by the sum of squares total, which is about 32,600. So the ratio will give us the R squared, which is indicated in the output. By way of interpretation, we would say that 58 or approximately 58% of the variation in the house prices is being explained by the variation in square feet. Or our regression model, which is this, explains approximately 58% of the total variation. We can also have or calculate the standard error of our estimates, and it is given as the standard deviation of the variation of observations, and is given as the SSE divided by the sample size minus k, which is the number of independent variables, minus 1. Because we are dealing with a simple linear regression, our k is 1 because there's only one independent variable. This sample or these standard errors would help us to determine the significance of our B1, that is the significance of the slope. It will help us also calculate the standard deviation, which we are going to use in other computations. So our standard deviation of the regression slope will be given as the standard error over the summation of x minus x bar all squared. So from the last example, we could see that our standard error was given as 41.3302, that is already calculated for us. And then the standard deviation of the errors was given as 0.03297. That is the standard error divided by the summation of x minus x bar all squared. Given this information, we can now make inferences about the slope. That is, whether there is actually a linear relationship or there is no linear relationship. If there is no linear relationship, we are going to test the hypothesis that B1 is equal to 0 against the alternate hypothesis B1 not equal to 0. That is when a linear relationship does exist. Our test statistic is such that T is equal to B1 minus beta 1 over the standard error of B1. Because we are testing against this one, or beta 1 being true, beta 1 is always equal to 0. Therefore, our test statistic is actually B1 over the standard deviation of B1. So let's make an inference about the slope for this test. We've already estimated that our regression equation is 98.25 plus 0.1098 times the squared feet. Therefore, our slope is 0.1098. We want to find out whether this model is actually fitting, or whether the square footage of the house affects the sales price, or whether the square footage of the house is a good predictor for the price of the house. And based on that, we formulate our alternate and our null hypothesis, where our null hypothesis says beta 1 equal to 0, and then our alternate hypothesis says beta 1 not equal to 0. Then we have our coefficients, the standard error of the coefficients, and then the t statistic. The t statistic is given as the value of the coefficient divided by a standard error, that is 0.10977 divided by 0.03291, which gives us 3.32938. So this becomes our calculated statistic as against the one we find from the table, which is a critical value, whose distribution is actually a t distribution with an n-2 degrees of freedom. Our sample size is 10, therefore our degrees of freedom is actually 8. So based on this information, we are going to have a critical value of plus or minus 2.3060. Remember that is two-tailed test, therefore alpha is divided into 2. Based on the value of this t statistic, you see that it is way bigger than 2.30, and hence is found within our rejection region, and therefore you decide to reject our null hypothesis and conclude that there is evidence that square footage affects the price of the house. We can also find confidence intervals for the slope, which we will say that the upper tail, or the upper limit for the confidence interval will be B1, that is the slope, plus or minus the t alpha over 2, that is the critical value, multiplying the standard error. So the upper limit is giving us the coefficient plus the critical value times the standard error. Then the lower limit is giving us the coefficient minus the critical value times the standard error. So based on this, we can also find the upper and then the lower confidence interval estimate for the regression slope. Now, as we said, the regression model can help us to also estimate or predict the price of a house based on a certain square foot. For example, assuming that we've already established that our model is well fitting and then our house size is actually a good predictor for house price, then it means that for a certain house with a certain size, we can predict its price. Therefore, we want to predict the price of a house with a size of 2,000 square feet. Based on the regression model, we said that house price is equal to 98.25 plus 0.10977, which has been rounded up to 0.1098 times the square feet. Since the square feet is 2,000, we put in the value of 2,000 in place of the square feet and solve, and we have 317.85. Remember that this is given in thousands, and therefore we say that the predicted price for a house with 2,000 square feet is actually $317,850. That means that since we've been able to establish a relationship between the size of a house and its price, we can now predict the price of a house given a certain size measured in square feet. So as we said, we can also predict the value of the price of a house based on its size. That is, if you have any value or if you have any house given the square feet or given the size, based on the relation we have here or based on the model we have here, we can predict its price. You can solve further examples given in your tutorial set and familiarize yourselves with a lot more of these regression models. Note that these were coming from Excel generated samples, and you can also solve these ones too by hand. This brings us to the end of session 13 and the end of UGBS 301. Thank you.